Welcome back. So we'll finish off lesson 2 with a look at performance and robustness uh, and an example of how performance can change with replication changes. So in this video, we're going to look at how robustness is achieved within HDFS and how you can change performance by changing a few parameters and then looking at an example of how that happens, but then how that affects robustness. So the first thing to look at is the common failures that happen when you have a Hadoop cluster. If you recall the design, we are looking at lots of nodes and disks. So one potential thing that can happen is essentially data node failures. So the server itself could fail, crash for some reason, or the disk can crash, and sometimes there's data corruption because of network issues or maybe a disk issue. So all of that could lead to a failure in the data node aspect of HDFS. You could have network failures, so you could have a network go down between a particular rack and the name node, and that can affect a lot of data nodes at the same time. You could have name node failures, disk failure on the name node itself, or the name node itself could run out of resources. So a lot of ways you could have an interruption on HDFS. And the design, as we saw before, is aimed at mitigating some of these. So the first mitigating thing is the name node actually has heartbeat reports from all the data nodes periodically. So here we have data nodes spread out over 2 racks, and you can see the connections back to the name node, and you get basically consistent heartbeat reports and block reports from the data nodes. So if this periodic heartbeat stops for some reason from a particular name node, so it doesn't, there's a timeout period essentially, and if the name node doesn't receive a recent heartbeat, it will mark the data node dead. And any new I/O that comes up is not going to be sent to that data node. Also remember that name node has information on all the replication information for the files on the file system. So if it knows if a data node fails, which blocks will fall below the replication factor. Now this replication factor is set for the entire system, and also you could set it for a particular file when you're writing the file. Either way, it knows, the name node knows which blocks fall below replication factor, and it will restart the process to re-replicate these blocks on other nodes that are still connected and active. So the other thing that happens is you might get data corruption. So that is mitigated using checksums. So when a file is created on a client, you get a checksum computed, and this particular checksum is stored in HDFS namespace. So when you go back to the read aspect and you're trying to retrieve this data, each block that is read, you have the checksum information available, so you would check that, and then if there's a problem, like if the checksum doesn't match, you reread from an alternate replica. Again, having the replica helps you get uncorrupted data in this case. The bigger failure is if the name node itself has an issue. So you could have metadata structures on disk on name node, which and the disk fails. So that's an easy one to mitigate by having multiple copies of this metadata structure. The other thing that can happen is the name node itself could crash or have some kind of problem. So that has two option of failing over to a standby name node. This is manual by default, so someone will have to go to it. So that's like a system administrator. In the current versions of Hadoop, this can be automated, but it's not done by default. So those are some of the robustness issues and how they are dealt with. Now we'll go back to the performance aspect and see, take one particular parameter. So in this case, we're going to change the replication factor and see how that improves performance. So the example we choose to show this is a distributed copy. So Hadoop has a distributed copy function which allows you to transfer a lot of files in parallel into HDFS. The example I've chosen is from one of the SDSC systems called Gordon, and what we did is essentially copy 32 files with a total data of 512 gigabytes. So it's half a terabyte of data essentially being moved into HDFS. And what we did is change the map and node counts and also change the replication to see how the copy performance is impacted. So the first table is essentially showing the distributed copy with the default replication. So that's replication set to 3. Remember, we are copying out of a parallel file system, so the read part of it is coming out of a non-HDFS file system, but it has enough performance to deal with this aspect. And then we are copying this into HDFS, which is built based on local solid-state disks on this machine. And what we did is increase the number of nodes from 8 to 32. You might wonder why I'm stopping at 32. It's because we have 32 files and it doesn't really make sense to go beyond that, especially with replication 1. So that's why we capped this as 32. The machine has a lot more nodes and you can actually go to a lot bigger size if needed. Now, one thing you'll notice is as you increase the map task with the same number of nodes, you get a little bit of better performance. So if you're looking at the 16 node case, you go from 220 megabytes per second with 2 map tasks to 387 megabytes per second with 8 map tasks. So that obviously matters. And then the other thing you notice is when you get up to 32 nodes, you're getting about 779 megabytes per second. So keep that number in mind because we're going to change the replication for the next case. So we do the same copy with the same set of files, and we say we're going to be brave and do no replication. This means all the disks on the 32 nodes are now available for essentially data writes of the primary blocks, and there are no replicas. And you can straight away see there's a huge jump in performance. And with 32 nodes, when all 32 disks are available, so you'll end up with basically 1 file on each disk. We get a huge performance gain, and we are almost seeing 3 gigabytes per second, which is more than 3x of what we saw with the replicated case. So clearly there's a big performance jump in the data copy part. Remember, there are trade-offs in all of these. I mean, one performance trade-off is that actually when you go out to do some of the map reduce jobs, having replicas gives additional locality possibilities. But the big trade-off is with robustness. So in this case, we said no replica. So what does that mean? Say you lose a node or a disk during this run, you can't recover because there is no replication. Similarly, with data corruption, if you get a checksum that's bad, now you can't recover because you don't have a replica. So there are always trade-offs. And this is just one example. There are lots of parameters, and you could have similar trade-off and effects depending on what you do. And as I mentioned in the previous module, there is a long list of parameters that you can go look at, and the link is in the previous video. So essentially what we saw is with the blocks, with some of these changes, you can impact performance, but there's a robustness trade-off. So in the next lesson, what we're going to do is look at more basic things like how do you access data on HDFS, some basic HDFS commands. We're going to look at output from commands that I ran on the Cloudera Quick Start VM. Remember, we did look at this in an earlier module, so please revisit those lessons if you want to get prepared for doing some of these Quick Start VM tests yourself, and then we'll have some examples. So see you next time. Thank you.